Welcome back, students. Today we'll be covering up the topic dynamics of uniform circular motion. Let's begin with the concept of centripetal force. Centripetal force is the force required to move a body uniformly in a circle. This force acts along the radius and towards the center of the circle. In fact, when a body moves in a circle, its direction of motion at any instant is along the tangent to the circle at that instant. As you can see in the figure, we can find the direction of motion of the body moving in a circle by drawing the tangent, and by observing the diagram itself you can understand very easily that the direction of motion of the body moving in a circle goes on changing continuously. According to Newton's first law of motion, a body cannot change its direction of motion by itself. An external force is required for this purpose. It is this external force which is called the centripetal force. On account of a continuous change in the direction of motion of the body, there is a change in velocity of the body, and hence it undergoes an acceleration called centripetal acceleration or radial acceleration. Now, we have already obtained an expression for centripetal acceleration in our previous sessions, and we had seen that it is given by A equal to V square by R or equal to R omega square, where V is the linear velocity, omega is the angular velocity of the body, and R is radius of the circular path. Now, as force F is equal to mass into acceleration, therefore centripetal force should be equal to mass multiplied by centripetal acceleration. So therefore F is equal to mv square by R, and that is further equal to mr omega square. So as I have already told you, the centripetal force acts along the radius and towards the center of the circle. Centrifugal force. The natural tendency of a body is to move uniformly along a straight line. When we apply centripetal force on the body, it is forced to move along a circle. While moving actually along a circle, the body has a constant tendency to regain its natural straight line path. This tendency gives rise to a force called centrifugal force. Hence, centrifugal force is a force that arises when a body is moving actually along a circular path by virtue of tendency of the body to regain its natural straight line path. Centrifugal force can be regarded as the reaction of centripetal force. As forces of action and reaction are always equal and opposite, therefore magnitude of centrifugal force is actually equal to mv square by R, which is same as that of centripetal force. However, direction of centrifugal force is opposite to the direction of centripetal force. That is, centrifugal force acts along the radius and away from the center of the circle. Now, centripetal and centrifugal forces, being the forces of action and reaction, act always on different bodies. For example, when a piece of stone tied to one end of a string is rotated in a circle, centripetal force given by F1 is applied on the stone by the hand. In turn, the hand is pulled outwards by centrifugal force given by F2 acting on it due to tendency of the stone to regain its natural straight line path. You can see the centripetal and centrifugal forces in the picture. Now, let us come to the applications of centripetal and centrifugal force. Rounding a level curved road. When a vehicle goes round a curved road, it requires some centripetal force. While rounding the curve, The wheels of the vehicle have a tendency to leave the curved path and regain the straight line path. Force of friction between the wheels and the road opposes this tendency of the wheels. This force of friction, therefore, acts towards the center of the circular track and provides the necessary centripetal force. In the figure that you can see on the screen right now, weight of the vehicle, that is mg, acts vertically downwards. R1, R2 are the forces of normal reaction of the road on the wheels. As the road is level or horizontal, R1 and R2 act vertically upward. So we can write down R1 plus R2 equal to mg. If mu is the coefficient of friction between the tires and the road, F1 and F2 are the forces of friction between the tires and the road directed towards the center of the curved track. Then we can write down F1 equal to mu R1 and F2 equal to mu R2. If V is the velocity of the vehicle while rounding the curve, then centripetal force required will be equal to mv square by r. As this force is provided only by the force of friction, so we can write down mv square by r is less than equal to F1 plus F2, which is further written as mu R1 plus mu R2. We can take out mu as common, so that will give us R1 plus R2. So mv square is less than equal to mu times R1 plus R2. So now we can write down mv square by r to be less than equal to mu times mg. Now if you remember, R1 plus R2 is equal to mg. So we have substituted over here in place of R1 plus R2 mg. So you can remove m from both the sides. So you get v square to be less than equal to mu rg. So therefore v will be less than equal to root over mu rg. Hence, the maximum velocity with which a vehicle can go round a level curve without skidding is given by v equal to mu rg under root. The value of v depends on radius r of the curve and on coefficient of friction mu between the tires and the road. Let's come to the next important topic, banking of roads. Now, just now we discussed that the maximum permissible velocity with which a vehicle can go around a level curved road depends on mu, that is the coefficient of friction between the tires and the road. The value of mu decreases when road is smooth or tires of the vehicle are worn out or the road is wet and so on. Thus, force of friction is not a reliable source for providing the required centripetal force to the vehicle. A safer course of action would be to raise outer edge of the curved road above the inner edge. By doing so, a component of normal reaction of the road shall be spared to provide the centripetal force. This phenomenon of raising outer edge of the curved road above the inner edge is called banking of roads. Now for this, you may refer to the picture that is coming on your screen right now. OX is a horizontal line. OA is the level of banked curved road whose outer edge has been raised. So angle XOA is theta and it is called the angle of banking. Weight mg of the vehicle going over the banked road acts vertically downwards. Normal reaction R of the banked road acts upwards in a direction perpendicular to OA. R can be resolved into two rectangular components, R cos theta acting vertically upwards and R sin theta acting along the horizontal towards the center of the circular track. If V is the velocity of the vehicle over the banked circular road of radius r, then centripetal force required F will be given by mv square by r. Now in equilibrium, r cos theta balances the weight, so it will be equal to mg. Let's mark it as equation 1. And r sin theta provides the necessary centripetal force. You can see in the picture. R sin theta provides the necessary centripetal force. So that should be equal to mv square by r. Let's mark it as equation 2. Dividing 2 by 1, we get r sin theta by r cos theta to be equal to mv square by r into mg. So you can cancel out m, you can cancel out r. So you are left with tan theta equal to v square by rg. Knowing v and r, we can calculate theta. So if h is the height AB, you can refer to this picture. If h is the height AB of outer edge of the road above the inner edge, and OA, that is the breadth of the road, is given by small b, OA is given by small b, AB is the height given by h, then we can further draw a simplified diagram for this. This is B, this is A, this is O, this is theta, this is B and H. So we can write down OB equal to OA square minus AB square, that is equal to root over B square minus H square. So tan of theta, that is equal to AB by OB, will be equal to H by root over B square minus H square. So from this equation and the equation written here, we get tan of theta equal to V square by Rg, and which is further equal to H by root over B square minus H square. From this equation we can calculate H. Now usually H is much smaller than B, therefore H square is negligibly small compared to B square. So we can write down tan of theta equal to V square by Rg, which is further equal to H by B, since we have neglected H square in comparison to B square. Roads are usually banked for the average speeds of vehicles passing over them. However, if the speed of a vehicle is somewhat less or more than this, the self-adjusting static friction will operate between the tires and the road, and the vehicle will not skid. The speed limit at which the curve can be negotiated safely is clearly indicated on the signboards erected along the curved roads. So we can get the expression for the safe speed V to be equal to Rg tan of theta. This is the simplified expression for velocity, as we have not taken into account the force of friction between the tires and the road. So when we consider the force of friction, we can obtain a modified form for the safe velocity. That is the velocity at which a curve can be negotiated safely. So let's do that. So the maximum permissible speed for the vehicle is much greater than the optimum value of the speed on a banked road. It is because friction between the road and the tires of the vehicle also contributes to the required centripetal force. So as the vehicle is moving along the circular banked road OA, force of friction between a road and tires of the vehicle, that can be written as F is equal to mu into R, and it acts along the direction AO. The force of friction can be resolved into two components. We can write down number 1, mu R sine theta along downward direction, and mu R cos theta along inward direction. Now there is no motion along the vertical direction, so we can write down R cos theta to be equal to mg plus mu R sin theta. If V max is the maximum permissible speed of the vehicle, the centripetal force is now provided by the components r sin theta and mu mg cos theta. So we can write down m v max square by r to be equal to r sin theta plus mu r cos of theta. Now from the previous equation, if we are marking it as 3 and this one adds 4, so from equation 3 we get mg to be equal to r cos theta, if we take it out as common, 1 minus mu tan of theta. Mark it as equation number 5. Also from 4, equation number 4, we have m v square by r equal to r cos of theta mu plus tan of theta. Mark it as equation number 6. Dividing these two equations, we get, that is 6 by 5, we get by gr, v square by gr equal to mu plus tan of theta by 1 minus mu tan of theta. Therefore, we get V max to be equal to root over, or we can put it as the power also. So we can write down Rg mu plus tan theta, 1 minus mu tan theta, and we can put the power to be 1 by 2. So it is under root rg mu plus tan theta by 1 minus mu tan theta. This equation actually gives the value for the maximum permissible speed for a vehicle on a banked road. Next we will be discussing about a situation that is bending of a cyclist. A cyclist provides himself the necessary centripetal force by leaning inward on a horizontal track while going round a curve. For this, let us consider a cyclist of weight mg. Now here, weight of the cyclist includes the weight of the cycle also. So when I am saying mg, that includes weight of the cyclist as well as that of the cycle. So let us consider a cyclist of weight mg taking a turn of radius r with velocity v. This radius is r with velocity v. In order to provide the necessary centripetal force, the cyclist leans through angle theta inwards, as you can see in the picture. The cyclist is under the action of the forces, number 1, weight mg, that is acting vertically downward at the center of gravity of cycle and the cyclist, and second, the reaction r of the ground on the cyclist. It will act along a line making an angle theta with the vertical. Now the vertical component r cos theta of the normal reaction r will balance the weight of the cyclist, while the horizontal component r sin theta will provide the necessary centripetal force to the cyclist. So we may write r cos theta equal to mg and r sin theta equal to mv square by r. So dividing these two equations, we get r sin theta divided by r cos theta, and that is equal to mv square by r divided by mg. So you get ultimately tan of theta equal to v square by rg. Therefore, the cyclist should bend through an angle theta given by tan inverse v square by rg, so as to have the necessary centripetal force while going round a curved path. It follows that angle through which the cyclist should bend will have to be greater if the radius of the curve is small, that is, the curve is sharper, and the velocity of the cyclist is large. It may be noted at this point that for the same reasons, an ice skater or an aeroplane has to bend inwards while taking a turn. We will continue with the next topics related to circular motion in our next session. Thank you.